Hello, folks. So, you now have some kind of a clue as to what's going on with Faraday's law. And you know how to figure out what the induced EMF is in a coil when you have a changing magnetic flux through the face of the coil. What Faraday's law doesn't do for you is to identify what the direction of the induced current is going to be. And so the theorem of sorts that exists that allow you to do that is wrapped up in what's called Lenz's law. The formal statement of Lenz's law is massively obscure. And so just hold on to the tabletop because here it comes. So you have an external magnetic field, you have a coil, you have an external magnetic flux through the coil, and that flux changes. When it does, it will induce a current. The induced current will produce its own magnetic field, which will produce its own magnetic flux through the face of the coil. The direction of the current, the induced current, will be such that the induced magnetic flux that it generates opposes the change in the external magnetic flux that started the process in the first place. How do you like them apples? So, if this was the way that Lenz's law was presented to you, and then you were asked to actually use it in a problem, you would probably just throw up your hands and just flip a coin, and heads you decide it was clockwise current, and tails you decide it was counterclockwise, and that would be it, and you just wouldn't hassle with it any further. It turns out, though, that there's sort of a shortcut way of approaching Lenz's law that makes the actual use of it quite simple. And so I'm going to give you the shortcut. And so let me get through here. So here are the steps. The first step is you want to identify the direction of the external magnetic field. Okay, how simple can it be? The second step is you want to identify whether the external magnetic flux is getting bigger or smaller. I mean, it can do this all sorts of different ways. The magnetic field itself could be getting bigger or smaller. The area of the coil could be getting bigger or smaller. In some way, shape, or form, the magnetic flux has to be changing. You have to decide whether it's getting bigger or smaller. The third step is a bifurcation. Okay, it depends on whether you're seeing an increase or a decrease in the external magnetic flux. If it's increasing, the induced magnetic field is going to fight the increase by being opposite the direction of the external magnetic field. And so you simply have to decide in what direction does the current have to flow so that you're going to get an induced magnetic field down the axis opposite the direction of that external field. And you can use that right hand approach where you lay the fingers of your right hand on the coil and your thumb points in the direction of the magnetic field. You've decided what direction that magnetic field has got to be. If the external flux is increasing, okay, if this is the direction of the external flux, this has to be the direction of the induced magnetic field. So you know what direction that has to be. You can figure out using the right hand approach what direction the current has to be to produce that magnetic field down the axis. On the other hand, if it happens to be decreasing, if the external flux is decreasing, once again, the induced current is going to fight the change. So it's not going to want to let it decrease as fast as it normally would. And the way it does that is by producing an induced magnetic field that's in the same direction as the external magnetic field. So the steps are pretty simple. You look to see what the direction of the external magnetic field is. You look to see if the flux is increasing or decreasing. If it's increasing, you know that that the induced magnetic field is going to fight the increase by being opposite the direction of the external field. If it's decreasing, you know that the induced magnetic field is going to fight the decrease by being in the same direction as the external magnetic field. And in both cases, you're going to end up using the little right-hand rule to figure out what the direction is. So here's an example. And I kind of jumped the gun, so let me go back. So here's an example. You've got a field. Go through the steps. So think to yourself what the steps are. What's step number one? Hopefully you said identify the direction of the external field. What is the direction of the external field? Hopefully you said to the right. What's step number two? Hopefully you said you identify the whether the external magnetic flux is increasing or decreasing. Which is it doing in this case? Well, you're told that the field is diminishing, so it's decreasing. If it's decreasing, what do you want the induced magnetic field to be doing? Do you want it to be going with the external magnetic field or against it? If it's decreasing, you're going to want it to be adding to the external magnetic field so that it doesn't allow it to decrease as fast. So you lay your hand on the coil in the appropriate direction so that your thumb is pointing in the direction of the magnetic field that you want, the external or the induced field, the magnetic field that you want. And from that, you're able to see what the direction of the current flow is. And in this particular case, it happens to be counterclockwise. So very quickly, here is just another example. I'm not going to do this whole example, but I'll let you just see it. You've got this coil. It's moving to the right into a magnetic field. In what direction is the induced current? So go through the steps. Pause for a second. Go through the steps. Okay, so you should be back from the pausing. Hopefully the steps that you went through, you said, what's the direction of the external field? It's into the page. Is the flux, is the external flux increasing or decreasing? It's increasing. What does that mean for the induced magnetic field? It means it's going to be opposite the external field, which means it's going to come out of the page. What direction does the induced current have to flow to do that? It's got to flow counterclockwise. Anyway, that's it.